Today's topic is reflection and the technology that's associated with reflection, and those are mirrors. Recall that when light strikes a surface, it can be reflected, absorbed, or transmitted. Reflection can be defined as a wave bouncing off of a surface. Light follows the law of reflection, which we'll get to, and is the subject of your lab. For the rest of this unit, we will be using the ray model of light, which means that we will represent the wave of light as a single ray without any wavefronts drawn in. So this would be with the wavefronts drawn in, but we're not going to do that. We're just going to use that simple black ray, and that's all. There are two types of light reflection, spectral and mirror-like. You can see spectral reflections from mirrors, calm water, and other smooth surfaces. The other type of reflection you can see from rough surfaces, like paper. By the way, the only reason you can't see anything is because light is reflected from it. Remember the lecture on illuminated light. As you can see from the spectral reflection on the left, reflected rays leave the surface at the same angle that the incoming rays struck the surface. This is also true of the diffuse reflections. It's just not as obvious. You can see every one of these. The blue is the incident ray, the red is the reflected ray, and if you follow it and you look at that N line, which stands for normal, you can see that the angle between the blue and the normal and the red and the normal is the same. Diffuse surfaces can become spectral surfaces. Just add water. This is a definition for your notes. Pause if you need to. And here's a second definition for you. Pause if you need to. Let's look at some of the terms and the symbols. The blue ray is the incoming light ray, called the incident ray. That's what the capital I is for. The red is the outgoing ray, or the reflected ray. This part's important. There's an imaginary normal line from the surface. Remember, normal means perpendicular. All the angles are measured from this line, not from the surface. They're measured from that line. The angle of incidence, or theta sub I in the diagram, is the angle between the normal line and the incident ray. This is important. Note, we are not going to measure from the surface to the incident ray, but from the imaginary normal line. The angle of reflection, or theta sub r, is the angle between the normal line and the incident ray. Take a moment and add this diagram and the definitions to your notes. Pause if you need to. And this brings us to the law of reflection, which is very simple. The angle of incidence is always going to equal the angle of reflection. Add that to your notes. Pause if you need to. And this brings us to the technology associated with reflection, and that is mirrors. We want to look at 4 different kinds of mirrors. Plane mirrors, spherical concave, spherical convex, and parabolic concave. First, some basics about all types of mirrors. The thing in front of the mirror is called the object. The image in the mirror is called the image. There are two kinds of images, virtual images and real images. Virtual images are images on the opposite side of the mirror. Add this to your notes if you need to. Pause if you need to. Real images from the same side of the mirror as the object. Add this to your notes if you need to. A better definition here would be real images can be projected. I think that's a better definition, because when we get to lenses, you're going to find that that's also true of real images formed by lenses. By the way, there are parallels between lenses and mirrors, and they both form real images, they both form virtual images, and using the definition real images can be projected holds for both of them. The first definition, that the real image is on the same side of the mirror as the object, it won't be true for lenses. I want to show you a real image. Here is a window looking out of a window, and you might recognize it. And what I've got is a setup down here, which is a little concave mirror and a card. Let me show you the mirror. It's concave. It's hard to tell, of course, from this, but concave mirrors, unlike convex and plane mirrors, can form real images. So we're going to form a real image with it. We're putting it here. It's facing out the window now, and so it's taking what it's seeing and projecting it onto this cardboard here, and I can move it back and forth and focus. And this is a real image. It's projecting, and I can touch it. So it's real, unlike the image you see when you're looking in a mirror and you see a virtual image. This is real. It's projected, and I can touch it. Notice it's upside down. Images formed by mirrors can be classified as either real or virtual, either upright or inverted, and either reduced in size, the same size, or enlarged. Let's look at plane mirrors. Plane mirrors are flat mirrors, are the most common mirrors and the ones you're probably the most familiar with. They're also not too interesting, but we kind of need to look at them. Note we have, again, the object is the thing sitting in front of the mirror. The image is the thing sitting behind the mirror. And also, please note the image is just as far behind the mirror as the object is in front of it. So technically, we don't say you're probably thinking, oh, it's a flat mirror, the image is on the surface of the mirror, right? No, the image actually forms behind the mirror, as far back as the object is in front of it. See how this is animated. So rays are leaving the object, they hit the mirror, then they reflect off the mirror, but to form the image, we have to take those rays back to the point where they cross and they form the image. So we can classify images formed by plane mirrors as virtual. Plane mirrors can't form real images. As upright, well, they're always right side up. You've never looked in a mirror and seen yourself upside down, have you? And as the same size as the object it's reflected. It does not reduce the object. It does not enlarge the object. They're always the same size. Convex mirrors are mirrors that bulge out. You've probably seen one in a convenience store. The reason they put them in convenience stores is because they have a wider field of view than a plane mirror, and so you can see more. They're also used as rear view mirrors for the same reason. They give you a wider field of view. And that's why it says so on the rear view mirror. It says objects in the mirrors are closer than they appear. Not all cars, by the way, do this, but the cars that do have that on there have convex mirrors as rear view mirrors. They do put that because everything we'll find out that convex mirrors always make everything smaller. They're also used in places like hospitals because people are rushing around all the time because there's emergencies. And there's a chance if you get to a corner where two hallways meet, people will run into each other. And the convex mirror, again, with the wider field of view, lets you see what's coming up in the hallway that you're about to cross before you actually get there. So if you see somebody's rushing down towards you, you can stop. So we can summarize the images of convex mirrors. They're always virtual too. They're not capable of forming real images. Just like the plane mirrors. That's why the demo of when I showed you a real image, I used a concave mirror, because neither of these, plane mirrors nor convex, are capable of making real images. The images are always upright, just like the plane mirror. But unlike the plane mirror, the images are always reduced in size. Okay, so these two mirrors are not that interesting. The one that's really interesting is the concave mirrors. So let's take a look at these. They're a little more interesting. They do just about everything. Okay, first we need a little more terminology. This is a diagram. MN is the cross section of the concave mirror. By the way, they're spherical in shape, so they're round if you in this cross section or part of a circle. So they're curved inwards. Think of them like a cave. Think of the word cave. So remember that these are the ones that are curved inwards. The C along the principal axis, which is that line running from the middle of the mirror backwards, is the center of curvature. If you were to draw this with like a compass, that's where you would put the compass point. F is the focus or focal point. V is the vertex or the center of the mirror. And the focal length is the distance between the vertex and the focus. Depending on where the object is placed in front of the mirror, the type of image formed and the location of that image will be affected. If the object is further away from the mirror than the center of curvature, as in this example, so again, C is the center of curvature, F is the focus. If I put the object anywhere further away from the mirror than the center of curvature, I'm going to get a real image. It's going to be inverted or upside down, and it's going to be smaller than the object was. It'll be reduced. If the object is at the center of curvature, I get something similar. I still get a real image. It's still inverted or upside down, but now it is the same size as the object. If the object is between the center of curvature and the focal point, I will still get a real image. It'll still be upside down, but it's getting bigger. It's not bigger than the object. So it's enlarged. And this one is pretty crazy. But if I actually put the object on the focal point, I get no image formed at all. If the object then is between the focal point and the mirror, then a virtual, upright, and enlarged object is formed. And this is why concave mirrors are used for makeup and sometimes for shaving mirrors. The concave mirror is also used by dentists to look at your teeth, so that the dentist will have an enlarged image of the teeth. Here's a summary of all the different types of image, size you get. And again, the image is in blue, the object is in red. Depending on where you put the object will determine what kind of image you get. So, okay, so remember in this case, number 6. Number 6 is showing that there's no image formed. So as you focus, so anything beyond the focus, anything this way, you're going to get a real image. Remember, it's projected. You could actually touch it. It's always going to be upside down. And starting with numbers 4 and 5 are enlarged. And then anything between towards the mirror, which is 7, 8, 9, you're going to get a virtual image. It's going to be enlarged. So this is where it's useful as a makeup mirror. So we're going to add this to our list now. So remember, so plane mirrors were always virtual, as were convex. Plane mirrors the image was always upright, as was convex. Plane mirrors, they only produce the same size image, and convex produce reduced image. But with concave mirrors, we get both real and virtual. We get both upright and inverted. We get both reduced size and same size and enlarged. So you can get any kind of image from concave mirrors. You should add this to your notes, by the way. If you need to pause, do so. Of course, we don't actually need a mirror to determine all this. There are actually ways to draw these, but we also can calculate this using an equation. First, we need some terms. D sub O, O for object, is the distance of the object. D sub I for image, is the distance of the image. F is the distance of the focus, or the focal length. H sub O again for object, is the height of the object. H sub I is the height of the image. And capital M is magnification. Here's the equation. 1 over F is going to equal 1 over D sub O plus 1 over D sub I. So if you know 2 of those, you can find the third. Also magnification. Now it makes sense that magnification would be the size of the image divided by the size of the object. So if my image is smaller, I'm going to get a fraction. If they're both the same size, I'm going to get a 1. So magnification of 1 means same size, no magnification. And if my I is greater than my object, I'm going to get a number greater than 1, and that means I'm magnifying to that extent. Okay. What might not be so obvious is that you can also find the magnification by taking the distance of the image divided by the distance of the object. And the last type of mirror we want to look at is the parabolic mirror. And the reason we have this is that concave and convex mirrors are spherical, and there's a problem with them. And that problem is called spherical aberration. The image defect of spherical mirrors, which does not allow parallel rays to converge at the focal point. It means images are fuzzy. And you can see here in this diagram where we have a cross section of a concave mirror, the incoming rays are coming in from infinity, and they get to the mirror, they bounce off the mirror. The black is the normal line. So for instance, this top ray here, and this one is its image ray, and it's the normal line. So this angle and this angle are the same. Okay. But notice that the further away we are from the center, the reflected images don't meet in the center. So if you actually look in these image mirrors, the edges are fuzzy. The image on the edges are fuzzy. How can we fix that? Well, that's where the parabolic mirror comes in. Instead of using a sphere, where a cross section was a circle, instead if it's a parabola, as in this picture, then all of the rays will meet at the focus and you get a nice sharp image. And this is the reason we use parabolic mirrors in telescopes, because we are seeing rays coming out from a distance, from infinity, and we want them to give us a nice sharp focus. And these are satellite dishes, by the way. They're also parabolic because radio waves, remember, light waves are electromagnetic waves, so are radio waves, and that's what these dishes are capturing, radio waves. They're going to do the same thing. They're going to bounce off that dish, and the idea is the actual pickup object is here. This is the receiver on all these dishes. The dish itself, all it does is reflect the rays off of it onto that receiver.